All right, everyone. So in this video, I'm going to go over the key points in study section 4.2.3, and they mostly go over the 4 types of chemical reactions. So this is a very dense study section, so I'm going to break it up a little bit. This will be a fairly long video. I will tell you when we have finished with part 1, which was Wednesday's assignment, and then when we're finished with part 2, which is Thursday's assignment. So there's 4 types of chemical reactions that we're going to be looking at, and the first one we're going to deal with is a synthesis reaction. Okay, and the general equation for a synthesis is going to be A plus B gives you AB plus energy. So what's happening in this equation is that you have 2 separate things that are combining to make one new molecule. And in that process, it is releasing energy, okay? When we have energy at the end there, this means it is releasing energy, okay? So if we have an example, we have Mg plus O2 yields MgO. Okay, so you can see there are 2 separate elements and they're combining to make one new molecule. Okay, and I'm going to come back to this in a second to explain the parts of this equation. But before I do that, I want to move on to decomposition, because decomposition is very similar to synthesis and it can help us understand. So a decomposition is sort of the opposite of a synthesis reaction. So instead of having 2 things combined to form one new thing, we have one thing that splits into 2 separate parts, okay? So our general equation is going to be AB plus energy gives you A plus B. So we have one thing that splits into 2 and it is absorbing energy. When we have energy on the reactant side, that means it is absorbing energy. Okay. So for example, we could have NaBr yields Na plus Br2. Okay, so the general idea here is not terribly difficult. It's just synthesis is 2 things combining. Decomposition is 1 thing splitting into 2. There is a little bit of a complication here, so I want to explain that. So they speak about in the apex oxidation states. And oxidation states, for our purposes, is just the same as the charge. Okay, so for example, if we have magnesium, let's look back on our periodic table here. We see magnesium, it's in group 2. Okay, and so it has a charge of plus 2. So now if we go back down here, magnesium has a charge of plus 2, so it has an oxidation state of 2. Okay, so that's pretty simple. We already know how to do this. The other thing that they mentioned is diatomic molecules. And these are molecules where the elements exist as pairs. Okay, and the elements that have this are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, or fluorine, okay? The way to think of this, the way to remember this is I pronounce this Brinkelhoff. That's just the way that I remember this. So this is something you'll have to look up or memorize. There's not really a reason for this. So for example, if we have bromine, if we have just bromine by itself, we're always gonna put Br2 instead of Br, okay? Because it is diatomic. So now, keeping those 2 things in mind, let's look back at our examples here. So when we're looking at this first one, we know magnesium is not diatomic. That's why it's just Mg by itself. But oxygen is diatomic. See, it's in our Brinkelhoff. Okay, so that's why it's O2. And then how did we get this MgO? Well, this we have to think back to when we were writing ionic equations. So we would say magnesium has a charge of +2, oxygen has a charge of -2, and remember we switch these numbers here. We would get Mg2O2, which simplifies to MgO. And in this case, you do have to simplify it. You can't leave it as Mg2O2. Now let's look at the other one. All right, how did we get that NaBr? Well, sodium has a charge of +1, bromine has a charge of -1. We switch our numbers, and we get Na1Br1. Great. Then we look over here, and we say sodium is not diatomic, and bromine is diatomic. That's why we have Br2, okay? So this is what part 1 goes over. Part 1 goes over what a synthesis reaction is, what a decomposition reaction is, and what those oxidation states and diatomic molecules are, okay? So if you want to pause your video now, you can, because this is all that you need to do for Wednesday. But I'm going to now move on to Thursday section, which is part 2. Okay, so now I'm moving on to Thursday section, part 2, and this starts off with single replacement reactions. Okay, and the general form here is that AB plus C yields AC plus B, or you could have AB plus C yields CB plus A. And in this case, we should see that C replaces either A or B, okay? So in a single replacement reaction, you have one compound of at least two things and one atom by itself, and it sort of switches places. And in this case, we always have that metals replace other metals, and nonmetals replace nonmetals. Okay. So now if we give ourselves an example, we have CuO, copper oxide, plus magnesium. We're going to have our magnesium is a metal, so it's going to kick out our other metal, which is copper, and we get MgO plus Cu. Okay? So how did we get all of these parts? Well, here we knew magnesium has a charge of +2, oxygen -2. You switch them, you get Mg2O2, which simplifies to MgO. So you do have to do this every time. And then we have to check with copper, and it is not diatomic. And that's why we wrote Cu instead of Cu2. Okay? There is one more complication to this, which is the activity series. Okay, so the activity series, this is a general rule that more reactive elements can replace less reactive elements, but not the other way around. Okay. So, for example, if we look at this, we have magnesium and we have copper. Okay. So to figure out if this reaction would actually happen, we would have to look at our activity series. So I have our activity series right here. Okay, so we were looking at magnesium and copper. And so since magnesium is above copper on the activity series, it is more reactive, so that means it can kick out copper. And that's why this reaction can take place, because magnesium is higher up on the activity series than copper. Okay, but this is something that we would have to check. So let's say if we have another example here, if we have CuCl2 plus Zn. For this case, we have copper and zinc we would have to compare. So we go back to our activity series. We find copper and we find zinc, and we say, okay, zinc is higher than copper. Zinc is more reactive than copper. So now if we go back down here, oops. Zinc is more reactive than copper, so that means it can happen. So I'm going to put a check mark. Okay? Because Zn is above Cu. Let's do another example. If we have aluminum plus calcium oxide. So here we're comparing aluminum and calcium. So for this reaction to happen, aluminum would have to be higher. So let's look back at our activity series. Here's aluminum, here's calcium, and aluminum is not higher than calcium. So this reaction can't take place. So I'm going to put an X here because aluminum is below calcium. So in this case, you're looking at the element that's by itself and the other metal elements, and you're checking which one is higher. And if the one that is by itself is higher in the activity series, then this reaction will occur. Okay? So this is everything we need to know about single replacement reactions. The general form, the way they switch, whether they're in diatomic or not, writing those equations out like we have before when we were in school together, and then figuring out, using our activity series, whether or not a reaction will actually occur. Okay? So now our last type of reaction is our double replacement reaction. Okay, so our general form here is going to be this AB plus CD yields AD plus CB. So here we should see, oops, okay, we should see that A and C stayed where they are, and B and D have switched places. Okay? So in this case, okay, so what happens is our metals and our non-metals switch places. So metals, again, replace metals, and our non-metals replace non-metals. And you get two new compounds. Okay. So let's do an example. Here we have AgNO3 plus NaCl. So here our silver is our metal, our sodium is our non-metal, and they're going to switch. Okay, so then we end up with our NaNO3 plus AgCl. Okay, and of course we would have to figure out our subscripts. So here we would say Na is +1, NO3, if you remember from our polyatomics, is -1. Those polyatomics don't go away. So it's Na1, NO3, 1. Okay, same thing. Silver, the charge of silver is +1, charge of chlorine is -1. We switch, we get AgCl. Okay? So we have to do this every time. All right, something else about these double replacement reactions is that there are 3 types. Okay, there's a precipitation, where a solid forms, in solution. So in solution means like we had two aqueous or liquids and then they form a solid. We have gas formation. This is pretty obvious. This is where a gas forms. And we have acid-base neutralization. And this one we don't really have to worry about right now because we're going to talk about that a lot more later. Okay. All right. So how we could look and determine what type our double replacement reaction is we have to look at our state symbols. So if we have an example here, let's say Na2SAQ plus 2HCl AQ yields H2SG plus 2NaCl AQ. Okay, here we would notice that we have two aqueous and then it produces a gas and an aqueous. So if it produces a gas, this is a gas formation reaction. Okay, pretty simple. Let's do another one. If we have something like this, running out of room here. AQ. Okay, so here we have two aqueous solutions and they combine and form a solid and an aqueous. So when we have something like that, where we have two aqueous or liquid type things and then they form a solid, this is called a precipitate. So this is a precipitation reaction. Okay. So identifying them is not very difficult. You just have to look at those state symbols to figure out if a gas is formed or if a solid is formed. And again, those acid-base neutralizations, we're not going to worry about identifying just yet. What becomes a little more complicated is if you have to predict the products. So if that is the case, then we need to use our solubility rules. Okay, so our solubility rules, they are a set of guidelines for whether a compound will form a precipitate. Okay, and these guidelines, you're always going to have them. I don't want you to memorize them, okay? So let's do some examples of just using our solubility rules. So let's say we're looking at LiCl. Okay, we're trying to figure out, is this going to be soluble or is this going to be insoluble and form a precipitate? So let's look up at our solubility rules. We have LiCl. Okay, so what I would say here is that, okay, I see compounds containing lithium are soluble. There are exceptions. It could be, and compounds containing chlorine are also soluble. So there are exceptions. So if we had like lead or silver or mercury, then it would not be soluble, okay? But since we have lithium, which is soluble, and chlorine, which is soluble, we can say this is going to be soluble. Okay, so now let's go back and write our answer. Soluble. And let's do one more example here. Let's say we have CaSO4, calcium sulfate. Go back to our solubility rules. And again, we're looking here at calcium sulfates. Okay, so we want to find anything about calcium or sulfate. All right, so I see here, compounds containing sulfates are soluble, so it seems like it's soluble. Let's look at the exceptions just in case. And we see calcium sulfate is insoluble because it's an exception. We always need to check our exceptions as well. So we're going to say this is insoluble. And if it's insoluble, that means that it will not dissolve, and that means it will form a solid precipitate. okay? So if we go back down, we can write our answer. Insoluble, it forms a solid precipitate, okay? So now let's do an example of a full reaction, okay? Let's say we have silver nitrate, AgNO3, and it's an aqueous, and we have potassium chloride, which is an aqueous. Okay, so the first thing we want to do is predict our products here, and we know our metals are going to switch places. So we're going to get KNO3 plus AgCl, okay? And again, we need to check that we have the right subscripts. Potassium is +1, nitrate -1, switch it up, K1, NO3, 1, so that's right. Okay, Ag is +1, Cl is -1, switch it up, Ag1, Cl1, so that's correct. And now we need to check solubility. Okay, so let's look at KNO3. All right, let's go back up here. All right, so we're looking at KNO3. So we want to find anything about nitrates or potassium. All right, I see here compounds containing potassium are soluble. All right, but now let's look at nitrates. Nitrates are soluble, okay? No exceptions here. The exception here is about silver, lead, or mercury, which we don't care about. So this is going to be soluble. So its state is going to be aqueous, AQ. Let's go back down. So this is aqueous. And our last part here, AgCl, okay? So now let's look back at our solubility rules. Okay, AgCl. So now we want something about chlorine or something about silver. And I see here that compounds containing chlorine are soluble. Okay, so that's good. Now let's look at the exceptions. Except these are insoluble if it has silver. So since it's an exception, this is going to be insoluble. So it's going to form a solid precipitate. Okay, so I can go back down and write that. It's going to be solid. So now let's add our state symbols, AQ and solid. And we find that since there is a solid right here, this is a precipitation. Precipitate is formed, so this is a precipitation reaction, okay? So when we're dealing with these double replacement reactions, we need to know that our metals and our metals switch, same thing with nonmetals and nonmetals. We need to know that we can use our crossing method to figure out our subscripts. We need to know that there are 3 types: precipitation, gas formation, and acid base. We can identify precipitation if a solid is formed. We can identify gas formation if a gas is formed. Then we need to know those solubility rules. Again, you don't need to memorize them, you just need to be able to use them. And then that can help us predict if a precipitate will form, right? So if both of these were aqueous, there would be no precipitate formed, so this reaction would not happen. But since one of them is solid, a precipitate is formed. So I know this was sort of long, but this is a video that goes over all of the parts of the 4 types of reactions: the synthesis, decomposition, single replacement, and double replacement. Please let me know if you have questions, and have a wonderful day.